Hey, do I need to put this on? Yeah.
我上午下午赛来的时候，我还跟他聊。This would be very nice day,
Clip it onto the outside of your pocket is usually easiest.
Okay.
Clip on the back, you can stick it in your pocket. Flip it to your belt, kind of. That's fine.
Do it here.
And then it's on me right now. I'll turn it on.
Okay, sounds good.
他跟有2个都分散。对对，在麦克上。Or just like some words here and there.
Motor skills. He's like walking well. He's like pretty good at applying motor skills for a baby. Too fast.
Do you want me to ring the bell again? It's very nice. I really like okay, we'd like to jump from 0 to like 3 months.
Yeah, my husband was like not excited about the newborn stage.
Like how small? Like you can hold them. I like it.
For like a month. And then they're like kind of like once they can hold their head, which like some days like my teacher gave me to hold stuff from like birth. Yes, for a while. But once they can do that, you're like
Sometimes easy.
yes, it's easier. And it's healthy. Because you like hold the something wrong, they're like got a broken hand.
Okay, let's start. So today we have a talk. Right now we have a talk by Zheng Xu. He's a research scientist at Meta, and previously he worked at Google Federated Learning in the Federated Learning team, and he works on privacy, optimization, and federated learning. Yeah, thanks.
Thanks for the introduction. I'm Zheng. Very glad to give this talk today. Today I will talk about synthetic, federated, personalized, heterogeneity here or there. So most of the presentation is based on my work at Google. I'm now at Meta, and I may talk a little bit about some of my personal interest and some of the ongoing or preliminary work at the end. So let's get started. So I want to get started with this like federated learning, very preliminary introduction again. As people in this workshop probably have heard about it several times now. So I will go directly into this. We bring this up like last year. Oh, it's 2026, so now it's 2 years ago, about the new definition of our federated learning. We see federated learning is a machine learning setting where multiple entities collaborate in solving a machine learning problem under the coordination of the server provider. A complete FL system should enable clients to maintain full control over their data, the set of workloads allowed to access their data, and the anonymization properties of their workloads. FL systems should provide appropriate transparency and control to the users whose data is managed by FL clients. So you may have heard about this definition from Dan's talk like a few weeks ago, and you may hear it again in Brandon's talk later in the afternoon. But this is a definition we brought up for the community to discuss. For this definition, we are not focused on actually defining what federated learning is or not is, but we want to emphasize that the property of the privacy values federated learning brought to, like these multifaceted privacy properties, including transparency and user control, data minimization, data anonymization, auditability, and verifiability. So along that, in the same paper, we also talk about like different stages or different properties of this federated learning. How do we view like this definition of these privacy properties in practice? The early stages is the kind of vanilla federated learning. If people talk about that, for especially at the Google context, we often talk about like the data stays on mobile devices, we only train a machine learning model with by transferring and aggregating gradients. Then later, this is a part that I will talk a little bit more in the later part of this talk, is what we call current federated learning. A lot of people also like to call it for private federated learning. It's essentially federated learning plus some more like privacy techniques, like secure aggregation, these encryption techniques, and differential privacy, these anonymization techniques. And I probably will only touch it a little bit, but you may hear it from other folks about what we envision, like this federated learning and the privacy property it can bring us in the future generations, in the ongoing development and the future federated learning. So let me talk a little bit about the current federated learning. It's a rather complicated status. This is just reflect the fact, like about now 3 years ago, we have this paper talking about how we apply the current federated learning techniques to a production application use case of GBOR language model training. So if you ignore all the like blue words, that's the conventional or vanilla federated learning where data stays on mobile devices. Then we only aggregate the gradients and use the aggregate gradients to update the model. So for the current federated learning, when we talk about the more privacy part, we will have secure aggregation. When we aggregate the results, we will also have differential privacy techniques. And more specifically, we developed a new algorithm so that the differential privacies can work in practice, especially when we have these complicated sampling, especially when we have the limited control over the sampling process of the devices. If you hear Ifer's talk Ifer's previous talk in the morning, you will know that the sampling and this privacy amplification is an important part to get a good privacy utility trade-off for applying differential privacy. So I don't think I will talk about the details about the DP algorithm we have. I will only mention the results we get, and I hope Brandon will talk about the technical details of the stateful noise mechanisms in the afternoon. But if not, I'll be happy to discuss offline, and you're more than welcome to look at our papers. So that's this part. So I want to show you some results from here. Like all through this talk, you will see a lot of results, hear a lot of maybe practical settings, experimental settings, but no equations. Until at the end, I will talk a little bit about some theory, preliminary work we did in plain language, not even a slide. So let's talk about this. I want to show you some results of the application of differential privacy in the production GBOR language models. Like it's a production setting, it's used by billions of people. If you use a Pixel phone, I'm almost sure you're using one of the models we trained. If you are using an Android phone, it's likely you're using it. But yeah, if you want to use it, just download the Google Keyboard applications. So we care about utility. We always measure it with strong utility in the A/B testing setting. And we always aim to better than n-graph-based models. These are older models we have in the application, all comparable with a no-DP version of the neural models. These are like conventional models we have trained with just federated learning. So this is considered strong baselines. One interesting is like we keep emphasizing and highlighting it that for making these differential privacy techniques practical in production, not too surprisingly, not too magically, like a lot of the other machine learning settings, one of the important things to get there is through scaling. We scale through computation is the key to get this good privacy utility trade-off. We use a lot more clients than previously used like in both industry and in academia, I believe. So that's the utility part. Now let's look at a little bit about the differential privacy. Yeah.
How do you define utility here when you say strong utility in A/B testing? What do you mean precisely?
So this is a production setting. We always, eventually we of course have some measurement like accuracy and other things, but eventually the main thing we care is the A/B testing. Like we deploy some of the checkpoints to some of the users and see how it affects the production metric. Like for this, it's usually including accuracy and measured by how these machine learning models help user typing, like the typing accuracy and typing speed, this kind of metrics.
But like your metric is an aggregate of accuracy and user satisfaction and others?
The metrics is aggregated, yeah, across a lot of mobile devices.
Okay.
Yeah. Yeah, maybe one thing to mention a little bit is that the metrics is aggregate a lot more than the devices I mentioned here. This is a device used in training, and it's a device used by, like in let's see, per round. So it's usually million scale, like, yeah. All right. So let's see here. We shows this figure is a summary, shows the DP guarantee we have for various models. For these applications, we train different small language models for different language and locales. And if you are interested in learning more, you can feel free to read the blog post for the simpler version. And I also linked the paper. That paper describes this advanced matrix factorization DP-FTRL algorithm, which help us get to really strong DP guarantees in practice. I see, and you may see that the DP guarantees for different languages may be different. And one of the main things is that these languages has different population size. There's so much we can do sometimes. And also for production practice, a lot of times the hyperparameters are not fully optimized. On one end, we did not count hyperparameter tuning into our DP guarantees. On the other end, in practice, we also don't tune it that much. So, yeah. And if you look at the purple bar there, that's the first production launch we have. As far as we know, the first maybe user level DP guarantee we achieved in practice in our industry. And then we improve it by doing some public pre-training. And for here, the public-private in our definition is like anything you can find on the web. We consider it's a public data. We use standard public data set collected already, the C4 data set for this case. And the private data is the real user data in production that we protect it with federated learning, differential privacy, and many other techniques in our system.
And utility is the same?
What?
Utility remains the same, accuracy is somehow...
Yeah, the utility measurement is basically what I said here. It's like for each model, we do A/B test. We look at offline evaluation first, then the primary decision is made by A/B testing. It should either be better than...
For these models, you say what the epsilon levels, privacy levels are. Is the performance equal across these models? While you improve the privacy, the performance stays the same?
Yes. When we improve that, we stay the same because we use the same measurement. Yeah. We always, when we have a new model, we always compare it with the old model to make sure that a lot of times it's slightly better. It's comparable, a lot of times slightly better because we kind of use newer batch of data. We did not do that definition in DP saying that this DP guarantee is for this period of user data, but effectively we only train it for a period, so for a certain time. Maybe. She's
So
first.
since Gboard has been around for a while, I have one basic question. So hyperparameter tuning is one sort of adaptivity, but you have probably hundreds of deployments over time. So do you like use a new data every time for like retraining a deployment, and like how much do the parameters transfer across these things? Like how should I like really view these numbers? Like if you have hundreds of deployments over time, and then each of these numbers is for like just one of them. There's like a lot of adaptivity in the process, which I don't know if you're accounting for or not.
So I think there are two parts of the question. One is the DP accounting part. Does DP count all this previous model release? Another is that the hyperparameter tuning part, right? So for the DP part, the short answer is no. We only account for the specific training run, but we also don't train it a lot. We will be mindful not training it extensively, and during this certain period of time, there is only one model that is trained and launched. So yeah, if we are very restrictive on that, we probably should limit us to the DP definition instead of user level. It's in user level in a specific period of time. But since we won't like we have to if we become really some adversary attacks, you can keep tracking all the model checkpoints and see how much information you can get from aggregating these all checkpoints. By the way, we don't have that many checkpoints, new checkpoints for each model. So answer that, the DP definition is more. If we be really restrictive, it's like a certain period of user level. And answer the hyperparameter question.
Yeah, that I think.
Yeah, we don't do a lot of tuning. Yeah.
I was just going to ask, what is that purple color indicating?
Okay, so this is the first DP guarantee we get for the model launch, for this Spanish model launch. We just tried it, and we get the results. That's epsilon about 8 also. Then the blue bars, all these blue bars are it's reported in this blog post. Oh, I think it's reported in the previous paper, like the main paper for this blog post. It's improved because we use public data for pre-training. So I think the intuition is that if you can learn something from the public data, you don't need to spend your privacy budget. A lot of this is a small language model. A lot of things you can just learn from public data. And this color is the light blue is from the advanced DP algorithm called matrix factorization. It's linked here. Yeah. So I'll go on. Let's see. This is basically what I said. We summarized all that in a blog post. We made a commitment for all next word prediction language models, and we have launched a large number of models across various languages. And as far as we know, it's one of the, we can proudly say it's one of the most large adoption of DP in production, and we even get some of the models with very strong epsilon smaller than 1.
Can you say a bit more on the scale of epsilon?
So
what is the value of epsilon?
So the y-axis is the epsilon. We use delta of 10 to the negative 10. And most of them is around 10 or below 10. That's where we consider in practice is somewhat acceptable at this level. Then for some of them, when we have advanced algorithms and the population is large, we want to see how much we can push it to. We can push it to epsilon 1 for some of the applications. Yeah. Yeah, and that's about 2 years ago, maybe less than 2 years ago. We have a new blog post talking about the synthetic data, which is the second part of the talk. But we also talk a little bit about the improvement or progress we made between the two blog posts for training these small models. For in addition to the next prediction language models, for all the production small language models trained on user data, we have federated learning with differential privacy guarantees. And we launched more models, and we have replaced all previous old models that only use federated learning without differential privacy. These are achieved with some new techniques. One thing is that the matrix factorization DP-FTRL algorithm is a little bit tricky to apply in practice, a lot more cost on system maintenance and all that. We developed a new algorithm which has the same strong privacy utility trade-off, but also ease of use in deployment in production. We also have a new network architecture that considers for a lot of the cross-device federated learning setting, we just use plain SGD on mobile devices for computation cost. And these language models usually work better with adhering. But if we make some changes to model architecture, it can also help for this training efficiency. And then the next part of this talk, I will talk a little bit more about the synthetic data approach. Start from synthetic data from large language models to improve pre-training, and also touches a little bit more about our research on synthetic data in general. So the first part, I will talk a little bit about the synthetic data via public language models post private training. This is one of the techniques I mentioned that improved our small language model training in general. So we start with asking a question there's this emergent trend of very large language models. By the way, we did this research 4 years ago also. At that time, it's late 2022, early 2023. It's a Nielsen large language model start showing a lot of promises. So we want to see if we can use this large language model to improve our small language models in production. We did a few things. We adapt some of the techniques for training large models, the public pre-training is a common practice. Use the tokenizers instead of the public tokenizers instead of customized private tokenizer we have. And then we did this of distillation from public language models with public data. And then the other technique we can probably ignore for now is distribution matching by data filter. It's for distillation, it helps a little bit on utility, but one of the interesting observations we have is significantly improve the data efficiency. But I guess it's somewhat reasonable. If we can distill from the large language models, even if it's just in the public pre-training stage, we only need a very small portion of data to get good performance, for both the pre-train checkpoint and for getting the good performance after the DP-FTRL fine-tuning. But distillation is not easy. We have to do inference of this live inference of large language models, and we have to do it on public language models. We want a method that is compatible with our already complicated current production pipeline, and a method that is easy to maintain in the future. Another consideration is these large language models show emergent generative ability. Can we leverage that? So this is kind of a simplified pipeline we already mentioned. We start from public pre-training, and then we will do DP fine-tuning. What we do in this work is that we simply replace the pre-training data. It's instead of pre-collected web crawled public data, we use synthetic data from large language models to see if we can improve and how far we can go with this. We use very simple ideas, not maybe somewhat also straightforward, intuitive. We use these prompt frozen large language models that we assume is trained from public data. The data source of these large language models is different topic. Like I mentioned previously, also through this talk, we consider all this web cloud available data as public data and user data on mobile devices as private data. So we do prompt to directly generate synthetic chat data. And we also have prompts to filter this public data set to see if they are good candidates to convert into chat-like conversation, which is an application we care about in these Google keyboard applications. So the method is very simple, and I'll just jump to some results. And this is a canonical figure we show of the results from this research. If you look at the x-axis, it's a federated learning training rounds. This is already after pre-training. This is a DP fine-tuning with in federated learning system. The y-axis, the eval accuracy, is also evaluated on the sample. It's a sampled user data, set of user data. So you will see these like oscillations on the curves. Like the blue curve is a baseline. It's basically what I described previously about how we train the models in early versions for production deployment. And the red curve is what we get from doing this synthetic data with public language models. At the pre-training stage, we significantly improve the performance. But another thing we found is maybe there are other ways to do it, but so far with this simple method, there's still quite a non-trivial gap between the performance from just public data with large language model help and the private data we can fine-tune with DP-FTRL, these private training methods. So if you see it, we will get some advantages on faster convergence and better performance. Eventually, all this will reflect in the privacy utility trade-off. So here are the values of all this. I'll just skip this. And if we look at the smooth curve, it's clearer that we can get faster convergence. So can we further improve the synthetic data? One last thing we did that actually also inspired our future research, I will talk in just a minute, is that we use small language models to filter. We use the fine-tuned small language models that have DP guarantees to further filter the synthetic data to see if we can improve the performance of the synthetic data just for the quality of the synthetic data per se. Because once we do that, then if we want to use that to do another round of DP fine-tuning, we should account for this DP budget we already spent for training that model. We can still improve, but not a lot. There's still a gap between what we can do with this public data, even with some limited private information from the small language models, and what we can achieve with DP fine-tuning. So yeah, so that's what I talk about. The last part is kind of the motivation for us to further see how much we can do with this kind of idea of small models with privacy guarantees and large public language models. We now call it a batteries module because that's the main purpose of the small module now is not to be deployed by itself, but to facilitate a large model and generate synthetic data to see how far we can go with that. And one of the main things we considered now is that we know that this can improve the quality of synthetic data in general. But we cannot beat these small language models, which can be directly DP fine-tuned. Now let's just switch the gear and see if we can improve some other models that we cannot directly tune with private data. We have some large language model applications, and we want to see how far we can go on improving that. So in a relatively newer paper, like we published last year, we talk about the ideas of, we train a small language models. We call it a batteries module. in this paper, we use the small language models because we already have it. Then we developed a method to further reweighting and filtering the synthetic data we have for different applications. Now, this is error correction applications on mobile devices. This is an advanced feature that use large language models instead of small language models that can be directly fine-tuned with federated learning and differential privacy. So that's the main idea, and I'll show you some of the results. Like, we have an original data set. This is collected, by the way, this is published at an industry track because all of this, we do it on a production model, and the data we cannot release. And it's also hard to be anonymized in some sense because we talk about billions of users for mobile applications. It's probably easy to guess who we are. So we intentionally get all this published. So unfortunately, all this cannot be reproduced in some sense unless you are at Google. Even at Google, it's probably hard. So, but let's see. We have some original data for that application. We have some lab held-out evaluation data set, of course. Then we generate synthetic data. We have the synthetic data from our previous work for small language models. Then we adapt it to error correction with help of the large language models, rewrite and all that for these large language model applications. Then we have the method to show that to do the filtering and all that, and to do the reweighting to improve the synthetic data. This result is already after the reweighting and the filtering. So the first line is the original results, this part is reported in an early paper for the production about how the performance are, and these are newer results. So there's a potential domain difference between the original data and our synthetic data, because one of the motivation of what we are doing this is we can make this synthetic data that's closer to the user typing application domain. And we have the second row is mainly use some hyperparameter tuning to improve the performance, and then we have this one as simple mix of the original data and synthetic data, so that we can gain the results for both words. Yeah. So. And this is some other explorations we did that because we generate synthetic data that is much larger than the original data, we have to manually craft it. So we start with basically use the synthetic data first as a pre-training step, and then do some mixed training. So these are offline evaluations. We also do the A/B testing and see some relative improvement if we use this synthetic data. So here's what we see about how we apply this synthetic data in practice for these large language model applications in mobile devices. It's used in machine learning kit, Gen AI API, which was announced last year, maybe a few weeks before we made this blog post. And this data used in the proofread feature. I believe it's now called a different. They have a different feature name, but you can still find the application. Okay. Now I'll talk a little bit more about the more fun part about the synthetic data work we have been doing. And while we are working on applying the synthetic data to improve the large language model applications, we also want to do some exploration to see how far we can go, what are better methods we can generates the synthetic data that represented the federated learning. We hired an amazing intern to work on this, like what happens in industry, like we work on the boring stuff, interns get work on the funny, interesting part. So yeah, let me first go back a little bit to why we care about synthetic data. We want to synthesize this privacy-preserving text data because this synthetic data has advantages in flexibility, and they also become a reusable component in complicated systems. By complicated systems, I mean it can either be the modern large language model training pipeline with pre-training, post-training, all this. Or now with mid-training is also a common practice with these various stages where you can all use, where high quality data can all be useful. It can also be like the system we build, like targeted for privacy preserving, but it's gradually it becomes relatively complicated. We have to acknowledge that. Nothing comes for free. To protect the privacy, we have to do all this. And for synthetic data, it can also help us to get joint. It's a very good way to bridge the public knowledge and the private domain information. And also another notable thing is like once you get this synthetic data, it can be examined, can be looked, and can be filtered. Enables possible difference in depth strategies for us privacy researchers. With all these strategies, with all these advantages, we want to generate this synthetic privacy-preserving data. There are a few ways in the literature how we can generate this synthetic data. I believe it's still the case. I made the slides last year, so probably need to add a few like 20-25 papers, including our own. But this is a literature, roughly still the literature. Fine-tuning is still the most effective way. And there's a line of algorithm called private evolution, basically use some statistics iteratively to refine, prompt, and select to generate synthetic data. Then there's also the inference, private inference kind of work, which without like changing the sampling process of the large language models, but doing more aggregation during inference time.
So like just here, like, for text data, like, what's your definition of privacy? Because like there's a whole literature in NLP on like author obfuscation. Right?
Yes.
And I mean, none of those approaches are used. Like they basically obfuscate text techniques and offer attribution systems.
Yeah, excellent question. Let's see, we all these like use a differential privacy definition, and for text, even differential privacy itself can vary a little bit because what's the exact unit you are using here. But I think that basically for all this work, we consider differential privacy as the main privacy technique. Yeah.
Differential privacy for text is a
What's a strong notion you
use differential privacy and you use that in a pipeline for author obfuscation. It's not competitive at all. Like it's you need a much stronger notion of privacy to privatize text. So like text is not just like you remove a token and that's what the differential privacy would do, right?
This is, just to clarify, this is user level differential.
Yes.
So this is like obfuscating
The user level.
bounding the contribution level of the user.
Oh, I
Not
see.
just an
I see.
example.
Oh, I see.
I wonder if that's the
I see.
So, I mean, in practice, like Sean and I, when I were at Google, we of course care more about user level. Down to all these papers, like a lot of times it's like just differential privacy, like for example level or a tricky like sequence level in it's not exactly one document a lot of times, but down to what's the training unit, the example unit in the training. This is not ideal, I will agree, but I think that's a separate topic. I believe there's a lot of ongoing discussion. Yeah.
I'm just saying, like in the text domain, there is a need literature privatizing text data. And I think like even at the user level, like if you use differential privacy, it's just not.
Yeah.
You know, like it will protect location or things like that. Like so, it's just very different.
Yeah, I agree. It's like a very active research direction on what we can do with the text privacy. But at this point, we still take differential privacy as granted. And in some sense, it's still one of the best. I mean, at least acknowledged like accurate or precise definition of what privacy means here in research. So, yeah. I think I'm short on time, so I'll move on, but happy to discuss more offline. So this is a method we proposed in this paper. This paper is like SML 2025. We start with like posing our intent to see how far we can push with a public language model and a small private privacy-preserving language models to get really good synthetic data. Then they come back with like surprising and even better algorithm is that let's just fine-tune a relatively small model. It's not that small. Eventually, it's about 100 million parameter size for the synthetic data generator, but it's small enough that we can see a lot of potential of this application in practice. So here's an improvement to the algorithm we have. Like we first still leverage the public data. We get a topic model on public data, and we use some continual pre-training. And at that time, continual pre-training is just a thing that has been named to improve with some public data, with a larger public data set to improve the 100 million generator we have. Then for the private domain, we first have a topic histogram as a condition as a first step. Then, based on this topic histogram, we will generate some keywords to feed into the continual pre-trained conditional generator we have to generate the corpus that is closer to the private domain. Note that we spent our privacy budget both in the DP fine-tuning step for the small models, because the model is small, so it's actually not that bad, and as well as the histogram. Because it's a histogram, it's statistics, the budget we spend there is basically negligible. It does not influence the final DP guarantee we have much. Then we can synthesize this data with both the keywords generated from the topic histogram and then use the conditional generator to generate the results. So I want to quickly show you some results. Let's see, we compare with various baselines. The upper bound of LoRa fine-tuning large generators for the synthetic data generation. And another upper bound, let's just directly train a downstream model with DP fine-tuning. By the way, this is all here shows the utility and the epsilon as well as you measures the privacy protection we have. The utility is measured by train a small language model on the synthetic data, or in this case, directly on the private data. So this is a application we care about, of course. And we compare with the private evolution baselines and some of the DP fine-tuning baselines, previous work that also used relatively small models. like GPT-2 style models that has similar size as our models. So yeah, so we get good results, especially when we have privacy budget. When we have privacy constraints for privacy utility trade-off. And if we don't consider privacy, of course, if we can just fine-tune on the private data, we still get quite good results. So is fine-tuning always better? Like that's basically our page, somewhat our page for the paper, but it's not always the case. Like say if we generate a very small set of synthetic data, then these private evolution algorithms then can help because we don't have enough data to do fine-tuning. So I probably won't have time to talk about this. Yuzheng is in the audience. Yuzheng this was our intern last year, did an excellent work on generalizing this conditional generator idea to like two parts, the conditional generator and the feature generator. This feature generator can be a topic model, like I mentioned before, or it can be a synthetic data generator by itself. So another interesting work Yuzheng did was to, let's see, in this framework, it allows us to further decouple the improvement of feature generator and the conditional generator. With this feature generator, we can use reinforcement learning algorithm to further improve the conditional generator. In this paper, we also have multiple measurements with similar downstream tasks as a utility, MOB score to measure the fidelity of the data, and another thing is somewhat motivates this work is all this distribution matching, the measurement for various attributes between the original private data and the synthetic data we have generated. And these figures show that with the IR algorithm, we can improve the conditional generator in various ways. So I'll skip this due to the time. And I think this is probably the last part of my talk. This is a heterogeneity workshop. What about heterogeneity? What do we think about it? Especially, let's say, if we consider the trend of, if you hear Dan's talk or the other Google folks talk about developing new techniques with trusted execution environment instead of transferring gradient. In this new paradigm and system, we may actually be able to transfer the data into this trusted execution environment. It's an extension of what we have as local devices. What about heterogeneity here? Let's see, for the federated learning part, the early days, we did a lot of research, did a lot of study. Even when these trusted execution environment are not possible, these federated averaging algorithms are surprisingly, or not too surprisingly, very effective in practice, particularly for our cross-device cross-device federated learning applications. At some point, we even write a paper trying to explain all this and alluded to maybe we need to think a bit more about what heterogeneity is, and there may be different paradigms of heterogeneity in practice. And let's see, even if we moved in a trusted execution environment, that gives us possibility to shuffling and mixing the data, but we may still have constraints about we are trying to get this differential privacy, particularly user-level differential privacy. Under such constraints, even in a data center applications, that you may still experience natural heterogeneity when we try to work with these privacy constraints. I did a little bit study of it myself in an early paper where we does not really consider federated learning constraints, but rather just user-level differential privacy itself. Another thing is that even with this trusted execution environment, the computation and communication cost would still persist. So the second part I want to bring is about the synthetic data. I talked a lot in this talk. It's already we already talked a bit use it to bridge the heterogeneity between public and private data. There are literature of existing work on using synthetic data to improve federated learning algorithms to tackle heterogeneity. And as you can see, for some of the works I mentioned for the synthetic data research, we actually leveraged this kind of heterogeneity to improve the diversity of the generation of this synthetic data. There's a lot of things potentially can be done. Like I write a little bit about this in the federated learning section of a synthetic data survey paper we put out recently. And finally, I think I'm at done. This is just a personal interest. I think there's a lot of, like always, there's a lot of opportunities and interesting problem for personalization. Like we, of course, did a lot of work in this space as a community for federated learning with these large language models. It opens a lot of new opportunities and also challenges. In a preliminary work, we did a little bit theoretical study actually for just out of curiosity to see, let's see, we want to do in-context learning for the reward modeling. And we show that if we just have a transformer, then let's see, it's basically impossible to use in-context learning to adapt to a new modality or new person. But if we introduce a little bit more information that can help to solve the theoretical challenge, and also a little bit advantage in the practical, empirical, preliminary study we have. This is a paper that we should release at some point, hopefully soon. So I'll stop it here. Thanks a lot for listening.
Thank you for your interesting talk. Any questions?
So in the part where you were using like synthetic data along with the user data, you mentioned some reweighing of the synthetic data. I was curious if this is to basically tackle heterogeneity, basically gaps in real user data, or are you trying to see what kind of user data tends to be memorized and like filling synthetic data there? Is there like some motivation of that sort there?
Our main motivation of synthetic data for most of the work I talked about is like domain adaptation. It's like the user data is in a different domain. Like we know it's really useful because if we can DP fine-tune a small model on it, we can get really good performance. That gap is not easily closed by just prompt large language models or use some simple techniques to generate synthetic data. So we want to get methods to see how much we can push the limits there so that we can generate synthetic data. Eventually, I would hope that by just training on synthetic data alone, it should be enough. So instead of we have to do pre-training and DP fine-tuning, we can maybe move some of the privacy protection techniques or this algorithm up in front for synthetic data generation. Then once we do that, this synthetic data can be as good as just the private data. That's just a hope.
Okay, we have a lunch break right now, and we will come back at 1:30.